Hello there, this is a video on Unit 8 titrations, acid-base, buffers. So we will be working some problems in a moment. I'll record on my iPad momentarily. Hello, this is a video on Unit 8 buffers, titrations, and main ideas. For a moment, you can pause this video and you can read this for yourself. So what is a buffer? There's two kinds. The first kind you're going to see on the AP test is a weak acid and a salt. The second kind is the one we're going to talk about, and that's going to be in a titration. It's going to be in a titration with, for this example, a weak acid, strong base, either hydrofluoric acid or acetic acid with a strong hydroxide. So we will see those examples in a moment. Obviously, you paused and read this, but working with millimoles and milliliters is a simplification that I use in my class. So not having to move back and forth with milliliters and liters and having millimoles instead of 0.001 molar, we say 1 millimolar. That's a time saver for the AP exam and probably in your class. I'm sure many teachers do the same thing. Okay, this is a picture. It comes from Michael Farabaw's videos in his series. He has great information. I'm just going to use his good picture. Okay, this example is different than the problem we're going to see. However, it's 0.2 molar sodium hydroxide, and there's several regions in a titration that we're going to talk about. His video shows this. So point E is the equivalence point, point C is the half point, and point A is just the pure weak acid, just a regular Ka expression. So we're going to see, I'm going to work through these. So problem number one. So the next page, this video is from Michael Farabaw's Unit 8 summative. It's about 1 hour, 101 to 106. You're welcome to click on that video, watch it, and we're going to work a similar problem. So here's his problem number 6, and we're going to work those different points. So point A is going to be just the pure weak acid. Points B, C, and D are going to be in the buffer region, close to the halfway titration point, and then point E is going to be the equivalence point, where it is not going to be a neutral equivalence point because we have a conjugate base. We will see it's going to be either fluoride or acetate, and we're going to do a Kb expression, which is notated right here in point E. So let's begin. So in this problem, a student titrates 50 milliliters of 0.64 molar hydrofluoric. When you multiply those together, you get 32 millimoles of acid. And as you add base, it's all about that base. 16 times 2 is 32. So obviously that's the equivalence point. And just looking at the graph, some AP questions just say, what's the region of the equivalence point? So it's about 8 or 9. And we'll calculate that in a few moments. So point A, again, you can pause this video anytime you wish and absorb this. Point A has 50 mils of 0.64 molar HF. Just do a regular Ka expression. pH is 1.7. Easy peasy. Point B, we start to neutralize some of the acid with some base to make some conjugate base. So we have a weak acid with its conjugate base. Now we're in the buffer region. Some people use the Henderson-Hasselbalch equation. I'm going to choose just to write a Ka expression, solve for the different molarities. You can see as we take the 32 millimoles of HF and we decrease them by 8, then we increase the volume, we change the concentration of HA, and we increase the concentration of A minus. So this is about a 3-to-1 ratio. 25% is a 3-to-1 ratio, and the pH goes up. It's going to raise the pH. Point C, we're at the half point. So this is a special point, and you can see that the molarity of the HA and the molarity of the A minus is equal. I've taken half those 32 millimoles, and I've got 16 millimoles of HF and 16 millimoles of F minus for a molarity of 0.276. Turns out that these values cancel, so the Ka equals H. Therefore, pH equals pKa. This is a very common question. And it turns out that when I didn't round, I got 3.14. Not really pi, but I love to see numbers everywhere. So this is a very important point of the titration. Okay, letter D, point D. Now we're having a little bit more base. So we have less acid, more base. Again, a 3-to-1 ratio, but it's a higher ratio of base to acid. Therefore, it's more basic. Therefore, it's higher pH, pH 3.6. And then now we have the equivalence point, and it requires a little bit more thought and effort. So the way I look at it is you've neutralized all of the HF, and now you have 32 millimoles of F minus in a new volume. So that's 66 milliliters, 16 plus 50, 32 millimoles divided by 66 is 0.4848. You've diluted it. And then Ka times Kb equals Kw. We're going to use a fluoride hydrolysis. The conjugate base is going to make HF and hydroxide. I will use a Kb expression for this. When I do, I get I'm sorry about this. I will fix that. It's 0.4848. So when I solve for hydroxide, it's 2.6 times 10 to the negative 6. The POH is 5.6, and therefore the pH is 8.4. Whew, that took a lot of work. And then finally, in letter F, we've increased the amount of base to 20 milliliters. Therefore, we have excess base. It's easy peasy. You have 40 milliliters of base, which is 8 millimoles excess. 8 divided by 70 is 0.114. Take the negative log, subtract from 14, and the pH is 13.1. So again, you can pause and absorb more of this, but I wanted to go through those points again. Point A is the pure weak acid. Points B, C, and D are in the buffer region. Point E is the equivalence point, and point F is the excess base. This is one example going all the way through of a weak acid, strong base titration. So now, in a moment, you're going to work the rest of this problem. Now you do one. Problem number 2. We have different molarities. So again, you need to find your millimoles, and then you need to increase the volume and change each point. So question number 1 is going to be show the calculations for A, B, C, D, E, F. There's room below. Number 2, what is a buffer? So you know what a buffer is. I'm just trying to refresh your memory. Number 3, B, C, and D. Look at points B, C, and D and discuss the buffer capacity and the buffer ratio and how it affects and what it means. So here's a piece of paper that you can, you'll download the PDF and you can handwrite this. There's a piece of graph paper like you would for a free response question. Here's letters A, B, C, D, E, and F. And there's plenty of room for this. So I'm going to feel free to show those calculations, and I will record the solutions in a moment or two. Good luck. May the force be with you.